What if black holes are not the strangest creations of the universe? What if even these titanic abysses are only the threshold to something greater in the vast silence of the cosmos? Black holes loom as the ultimate enigmas. They swallow light, devour time, and bend the fabric of space until meaning itself begins to collapse. They are born from the violent deaths of massive stars, yet they become something far beyond death. They become prisons where cause and effect are torn apart for centuries. Humanity has gazed at the night sky and believed the universe could be mapped by reason. But black holes remind us that there are places where reason is no longer enough. They stand like dark monuments in the void, their horizons marking the edge of what can ever be known. To cross that line is to surrender every law of physics we understand. And yet, a question lingers like a shadow behind them. If black holes are only guardians, then what secrets lie behind their gates? If these collapsed stars are not the strangest things the cosmos has shaped, then what worlds, what forces, what truths wait beyond? The universe has never promised us comfort. It has only promised wonder. And tonight, we descend into the mystery, not of black holes alone, but of what may lie deeper still. The story of black holes begins long before they were ever seen. It begins with an idea, fragile at first, whispered by the mathematics of an age when telescopes were blind to such depths. In 1784, the English natural philosopher John Michell posed a question to the Royal Society. What if a star so massive, so dense, could exist that its gravity would be strong enough to prevent even light from escaping? In Michell's imagination, light itself was like a stone thrown upward, slowed by gravity, and pulled back if the well was deep enough. His thought experiment became the first shadow of what we would one day call a black hole. A few years later, the French mathematician Pierre-Simon Laplace reached the same conclusion. He suggested that nature might contain dark stars invisible to the eye, hidden in the silence of space. For their time, the idea was too radical, too disconnected from observation. It would fade into obscurity, waiting for the physics of the 20th century to resurrect it. It was Albert Einstein, in 1915, who bent the universe into a new shape. His general theory of relativity replaced Newton's force with geometry. Space itself could curve, and time could flow differently depending on where one stood. A year later, Karl Schwarzschild, while serving on the front lines of the First World War, found an exact solution to Einstein's equations. It described a point of infinite density, a horizon beyond which nothing could return. The mathematics was exact, undeniable, and terrifying. Einstein himself doubted such objects could exist in reality. He saw them as curiosities of the equations, not the destiny of stars. Yet the universe had already been preparing its testimony. In the middle of the 20th century, astronomers began to detect strange signals from the skies. In 1964, a bright X-ray source in the constellation Cygnus was discovered by a team led by Riccardo Giacconi. It was later identified as Cygnus X1, a binary system where an unseen companion siphoned matter from a nearby star. The invisible object was massive enough to suggest the presence of a black hole. For the first time, the shadows that Michell and Laplace had imagined, and that Einstein had doubted, were revealed in the heavens. But Cygnus X1 was only the beginning. By the late 1960s, radio telescopes uncovered quasars, brilliant beacons shining from the edge of the observable universe. Their power dwarfed entire galaxies, their light born from the violent hunger of supermassive black holes at their cores. The voids were no longer rare, isolated monsters. They were central engines of creation, sculpting galaxies, shaping the cosmos itself. Still, the search for proof continued. In 2015, the twin detectors of the Laser Interferometer Gravitational Wave Observatory, LIGO, heard a faint ripple in the fabric of space-time. Two black holes had spiraled together and merged, releasing more energy in a fraction of a second than all the stars of the observable universe combined. The signal lasted less than a heartbeat, yet it confirmed what had once been a speculation on paper. Black holes were not only real, they were loud. They were cosmic events that shook reality itself. Each discovery deepened the mystery. For every black hole confirmed, stranger questions emerged. Was the black hole the final word in stellar death, or just one among many fates the universe could invent? The deeper astronomers looked, the more exotic possibilities arose. Neutron stars, remnants of collapsed suns smaller than black holes but denser than atomic nuclei, were discovered through their rhythmic signals. In 1967, Jocelyn Bell Burnell, a graduate student in Cambridge, noticed a strange, repeating pulse in the data of a radio telescope. At first it was jokingly called LGM-1, Little Green Men, but the signal was not artificial. It was the beacon of a pulsar, a neutron star spinning hundreds of times per second, sweeping its magnetic beam like a cosmic lighthouse. Her discovery revealed that stellar death could produce not only silence, but rhythm. From neutron stars came magnetars, even rarer, their magnetic fields trillions of times stronger than Earth's. A single magnetar flare could outshine a galaxy, a cosmic detonation from a star no wider than a city. Here, matter was crushed so tightly that atomic structure itself collapsed, and the very laws of physics trembled at their edges, and the speculations did not stop there. Physicists began to wonder about even stranger entities. Boson stars, hypothetical objects composed of exotic particles. Dark matter halos, invisible structures that bend galaxies yet refuse to emit light. And in the most radical proposals, naked singularities, points of infinite density exposed to the universe, unshielded by an event horizon. Roger Penrose argued for the principle of cosmic censorship, suggesting nature itself must hide such singularities behind horizons. But what if nature did not always obey that law? Subramanian Chandrasekhar had shown decades earlier that there was a limit to the mass of a star's core. Beyond that limit, collapse was inevitable. The path led either to neutron stars or to black holes. Yet in the mathematics of collapse, other strange attractors lingered, whispering that black holes may not be the only monsters waiting in the dark. The history of black holes is therefore not a straight path from theory to certainty. It is a spiral, circling ever deeper into questions more unsettling than the last. First came the idea of invisible stars. Then came the proof of collapsed suns feeding on companions. Then the roaring quasars at the edge of time. Then the ripples of mergers echoing through space-time. Each step pulled humanity closer to an unsettling possibility. That black holes, long feared as the ultimate end, might not be the strangest children of gravity. That behind them, alongside them, perhaps even within them, are objects stranger still. The discovery of black holes did not close the chapter on cosmic mysteries. It opened the door to a library of deeper enigmas. And now the question lingers. If black holes are not alone in their strangeness, then what else has the universe hidden in its dark and silent halls? For generations, black holes were thought to be the edge of the possible. They were the ultimate expression of gravity, a place where the known laws of physics folded in on themselves and surrendered to silence. Even Einstein resisted the thought of their existence, regarding them as curiosities of mathematics rather than creatures of reality. To believe in black holes was to believe in a cosmos that could host impossibilities, and yet, impossibility became fact. The event horizon, an invisible boundary beyond which light itself could not return, was no longer a theoretical horizon on paper. It was a line etched into the universe. Cross it, and causality ends. Within it lies the singularity, a point where density becomes infinite, where space-time tears, and where equations dissolve into meaninglessness. The discovery of black holes shook physics at its foundation. Here was not only an object, but a paradox standing in the sky. The paradox of a horizon that traps light but still obeys relativity. The paradox of a singularity that no mathematics can tame. The paradox of the information paradox itself. Stephen Hawking's revelation that quantum mechanics and relativity may be locked in contradiction at a black hole's edge. If information that falls into a black hole is lost forever, then quantum theory, the most successful framework of modern physics, begins to unravel. If information somehow escapes, then black holes are not the silent prisons they appear to be. Either way, reality is understood through human science fractures. For a time, black holes seem to stand alone as the universe's greatest violation of reason. But nature did not stop there. From the remnants of dead stars emerged neutron stars, born in supernovae where matter is crushed to unimaginable densities. Inside them, protons and electrons are forced together, creating seas of neutrons so densely packed that a single teaspoon of their substance would weigh more than a mountain. Here, matter behaves as it does nowhere else, a quantum fluid bound by gravity at the edge of collapse. What black holes hide behind horizons, neutron stars reveal in the open. Their physics is not infinite, but it is extreme enough to defy intuition. In 1967, when Jocelyn Bell Burnell detected the first pulsar, the universe revealed its first glimpse of these strange corpses. A star no larger than a city, yet rotating with clockwork precision, sweeping a beam of radiation across the cosmos. The signal was so regular it was first suspected to be artificial, a message from another intelligence. Instead, it was the voice of matter pushed to its limits, a stellar heart still beating after death. Neutron stars were only the beginning of the shock. Among them are the magnetars, the rarest kind of stellar remnant. Their magnetic fields are the most intense known in the universe, trillions of times stronger than Earth's. So strong that if one were as close as half the distance to the moon, it could erase the information in every hard drive on Earth. These fields are so violent they twist the crust of the star itself until it shatters, releasing flares brighter than 100,000 suns. In 2004, such a flare reached Earth from 50,000 light-years away in the constellation Sagittarius. It struck our planet's atmosphere with a force that briefly altered its chemistry. If the magnetar had been closer, life itself might have been erased in a single silent flash. Such discoveries forced scientists to admit a chilling truth. Black holes were not unique in their power to rewrite reality. Other objects born of the same cosmic crucible carried their own forms of strangeness. Each one seemed to bend the laws of physics in ways that left human understanding trailing behind. The shock deepened when quantum theory and relativity were forced to confront each other inside these stars. Neutron matter, magnetar fields, and the extremes of density created laboratories that no earthbound machine could ever reproduce. Here, gravity crushes quantum mechanics, and quantum mechanics resists in ways that science has yet to fully grasp. Theories of exotic states of matter, quark-gluon plasmas, strange quark matter, or even phases of matter yet unnamed, might live inside neutron stars. If revealed, they would overturn the table of physics just as surely as black holes once did. But perhaps the greatest shock lies in what these objects imply. Black holes were once feared because they seemed to represent the ultimate limit. Nothing more extreme could exist. Yet neutron stars and magnetars prove that nature's imagination is not so easily bounded. It can forge city-sized bodies of unimaginable density, magnetic monsters capable of erasing entire worlds, and perhaps even stranger entities waiting unseen. Some scientists whisper about boson stars, hypothetical objects made not of ordinary matter, but of ultralight particles that might also explain dark matter. Others consider the possibility of naked singularities, singularities exposed to the cosmos without the cover of an event horizon. If such objects exist, they would not simply challenge relativity. They would tear away the curtain of cosmic censorship itself, exposing infinities to the naked eye of the universe. To contemplate such possibilities is to face a deeper unease. Black holes, as monstrous as they are, carry with them a strange comfort. They are contained by their horizons, hidden from direct view. Their violence is shielded behind a boundary that nothing crosses. But neutron stars, magnetars, and hypothetical naked singularities offer no such comfort. They reveal their strangeness openly, like scars written into the fabric of space. This is why some scientists confess that alternatives to black holes are even more disturbing than black holes themselves. A black hole may represent the end of matter and light, but its paradoxes are hidden from sight. A magnetar's violence, by contrast, can reach across the gulfs of interstellar space. A neutron star's density can be measured, its pulses heard like drums in the night. These are not hidden infinities. They are real, measurable, and dangerously near. The scientific shock, then, is not only in the discovery of black holes, but in the realization that they may be only one chapter in a larger story of impossibilities. The universe is not content with a single enigma. It multiplies them, scattering them across the sky like riddles written in fire. The paradox of black holes shattered the confidence that the cosmos could be neatly explained. The discovery of neutron stars and magnetars deepened that fracture, suggesting that the strangeness of nature is not confined to horizons, but woven throughout the stars themselves. Every new revelation widened the gap between expectation and reality. What once seemed impossible is now common. What once seemed singular may in fact be many. And with each step, humanity is left to wonder. If black holes are not the only objects that bend the rules of reality, then what other surprises wait, still hidden in the silence of the night sky? The universe rarely reveals its secrets in full. It offers signals, faint and fragmented, whispers carried across the void on beams of radiation, pulses of X-rays, and the trembling of space-time itself. To follow those whispers is to walk a path of uncertainty, where each clue leads not to clarity, but to deeper questions. Astronomers have long turned their instruments toward the sky in search of these signs. Radio telescopes trace the rhythmic beats of pulsars, their spinning hearts flashing like cosmic lighthouses. X-ray satellites catch the high-energy flares of matter falling toward unseen companions. And now, gravitational wave detectors listen for the distant collisions of compact objects, their mergers ringing like the final chords of a cosmic symphony. These tools, sharpened by decades of innovation, have carried us to the threshold of a new realization. Not every signal belongs to a black hole. Not every observation fits the models we know. Pulsar timing, once thought to be among the most precise clocks in the cosmos, has revealed subtle irregularities. Some pulsars slow or speed their rotation in ways that challenge neat explanations. Others quake, their crusts cracking under pressures beyond imagination, producing glitches that ripple through their signals. In some cases, the behavior defies the physics of conventional neutron stars. Could it be that within these tiny lighthouses are cores of stranger matter, hidden from sight but felt in their rhythm? Gravitational waves have carried their own hints of anomalies. The first detections from LIGO confirmed black hole mergers of staggering scale. But later signals suggested objects whose masses fell into a strange gap, too heavy to be ordinary neutron stars, too light to be the black holes predicted by stellar collapse. The gap became a riddle, a category without a name. Were these the echoes of black holes formed in unexpected ways, or the signatures of exotic stars never before confirmed? The possibilities multiplied in the realm of theory. Quark stars, bodies where the neutrons themselves dissolve, releasing seas of quarks bound by the strong nuclear force. Strange stars, composed of an even rarer form of matter, where strange quarks mix with up and down quarks in a new state of stability. Some have speculated about preon stars, hypothetical objects made of particles even smaller, beyond the reach of current physics. Each possibility is an invitation to imagine matter not as we know it, but as it might be in forms hidden by the veil of collapse. Observations tease at these possibilities. X-ray emissions sometimes suggest densities greater than those explained by neutron stars. Thermal signatures fade too quickly, as though cooling were governed by processes beyond nuclear matter, and certain bursts of gamma rays defy classification, their violence suggesting mechanisms more complex than magnetar flares or collapsing black holes. The deeper the investigation goes, the less certain the answers become. Every anomaly could be explained by unknown details in familiar physics, but each anomaly could also be a glimpse of something entirely new. The cosmos does not yield these secrets easily. Signals are faint, distorted by distance, and buried in noise. A gravitational wave crossing billions of light-years arrives weaker than the vibrations of an atom. An X-ray burst lasts for seconds, then vanishes, leaving only fragments for reconstruction. Pulsar glitches may repeat across centuries, a patience beyond human timescales. And yet, scientists persist, assembling patterns from fragments. They chart the timings of pulsars with exquisite precision, using them as a galactic scale detector to search for gravitational waves from supermassive black hole pairs. They monitor the skies with fleets of satellites, from NASA's Chandra X-ray Observatory to ESA's XMM Newton, mapping the invisible universe. They extend the reach of gravitational wave observatories, tuning LIGO, Virgo, and Kagra to sense ever fainter tremors. The effort is not only technical, but philosophical. It forces a reckoning with the limits of classification. If a compact object does not behave like a black hole, yet is too dense for a neutron star, then what language does science have for it? Labels like quark star or strange star are scaffolding, attempts to frame the unknown in familiar terms. But perhaps the truth is stranger than any name we can give. The anomalies accumulate like stones at the edge of a path, a pulsar with irregular spins, a merger signal from an object of impossible mass, a gamma ray burst without a clear source. Each alone could be dismissed. Together they hint at a pattern not yet understood. It is here that the search becomes unsettling. Because if these strange compact objects exist, they may represent not the exception, but the rule. Perhaps the universe is filled with forms of matter that lie beyond human imagination, waiting for the right eyes to see them. And so the investigation deepens. Every telescope, every detector, every equation becomes part of a larger effort to map a cosmos that refuses neat order. The search is not only for black holes, but for the family of shadows that surround them. Objects born of collapse, yet shaped by physics still unknown. Somewhere in those shadows may lie the true boundary of matter. Not the event horizon, but the point where the very concept of matter dissolves into new states of being. The universe, it seems, has not finished its story of compact objects. It has only begun the next chapter. The deeper humanity peers into the dark, the more it realizes that black holes may not be the strangest inhabitants of the night. There may be quark stars burning quietly in the silence, strange stars cooling faster than neutron physics predicts, preon stars too small to see, yet dense enough to reshape the understanding of the particle world. The search continues not because answers are near, but because questions refuse to rest. The cosmos resists simplicity. Its signals arrive as riddles, and its riddles lead to realms beyond imagination. The deeper investigation reveals not clarity, but wonder. A wonder tinged with unease, for if black holes are not alone in their strangeness, then reality itself is more unstable, more fluid, more alien than science once believed, and still the night waits, patient and silent, holding its secrets until the next signal arrives. Black holes were once thought to be the final word in cosmic strangeness. A star dies, collapses under its own gravity, and becomes a silence from which nothing escapes. They bend time, warp light, and guard their secrets behind an event horizon. Terrifying, yes, but in their terror there is also a strange familiarity. They are still born of stars, still tied to matter and energy that can be measured, modeled, and, in some sense, imagined. But what if collapse could take another form? What if the universe allows not only black holes, but stranger things, creatures of gravity and energy that defy the very logic of causality itself? One of the most unsettling possibilities is the naked singularity. A singularity is the heart of a black hole, the point where gravity crushes matter into infinite density. General relativity predicts it, but always with a caveat. The singularity is hidden behind an event horizon, a veil that shields the rest of the universe from its infinite extremes. This veil is the principle of cosmic censorship, proposed by Roger Penrose. It suggests that nature forbids the naked exposure of singularities. But if that censorship can fail, then a singularity could exist in open view, not buried within a horizon, but bare and unshielded. A point of infinite curvature revealed to the cosmos. The very thought breaks the spine of physics. If a naked singularity were visible, the rules of cause and effect would disintegrate. Paths of light could loop unpredictably. Time could fracture into multiple directions. The laws that give structure to the universe would become unstable. What would it mean to live in a cosmos where such objects exist? Would reality itself lose coherence from these unsettling speculations? The mathematics of Einstein's equations offers another possibility: the white hole. If a black hole swallows matter and energy, never allowing return, then a white hole is its time-reversed twin. It cannot be entered, only exited. It would spit matter and light into the universe, a fountain instead of a drain. No observation has yet confirmed such an entity, but the equations allow it. Some theorists have even suggested that the Big Bang itself might be understood as a kind of white hole, a singularity erupting matter into time. If so, the entire universe could be the echo of a process mirrored by the collapse of stars elsewhere. Beyond white holes lies an even deeper riddle: wormholes. These are bridges predicted by the mathematics of general relativity, tunnels through space-time that connect two distant points, or perhaps even two universes. They require collapse and curvature more extreme than black holes alone. In some models, black holes and white holes can be connected, forming the mouth and exit of a wormhole. Such structures would make the universe a labyrinth of hidden corridors. Travel through them would be perilous, requiring forms of matter and energy not known to exist. But if stable wormholes could be real, they would undo the very notion of distance. A journey across light years could collapse into a single step. The thread that binds these possibilities together is exotic matter. Ordinary matter obeys the familiar rules. Mass is positive, energy densities are constrained, pressure follows predictable patterns. But the mathematics of wormholes, of white holes, of even certain models of naked singularities demands matter of a different kind. Negative energy densities, phantom matter, substances that repel rather than attract. Such matter has never been observed directly, but quantum physics does hint at its shadow. In phenomena like the Casimir effect, negative energy appears in microscopic form. If the universe can scale such effects upward, then perhaps exotic matter is not only possible, but already woven into the fabric of space. If these objects exist, if naked singularities shine, if white holes erupt, if wormholes pierce the night, then black holes, as terrifying as they are, become almost comforting. Black holes hide their strangeness. They give us boundaries, horizons, places where physics ends but does not spill out. They are monsters, yes, but monsters we can place in cages. These other objects are different. They refuse boundaries. They expose infinities. They rewrite causality. They open exits from our universe or entrances from others. They threaten not only matter and energy, but the very concept of a stable reality. This is the escalation of the mystery. It is not only that the universe contains strange objects, it is that the spectrum of strangeness has no end. Each discovery leads to something deeper, more alien, more disquieting. Scientists attempt to model these possibilities, to keep them confined to equations and simulations. But in doing so, they admit the possibility that the universe is far stranger than even the boldest theories can contain. A black hole bends space and time. A naked singularity tears them apart. A white hole reverses the arrow of matter. A wormhole discards the meaning of distance. Exotic matter defies the very concept of what it means to exist. If black holes are guardians at the edge of the known, these other constructs are the shadows beyond the gates. They are not simply terrifying, they are alien to thought itself. To confront them is to wonder whether the universe in its deepest layers is built upon rules at all, or whether rules are only the fragile scaffolding of our limited perception. The night sky, serene to the eye, may be littered with such possibilities, and if one day they are confirmed, the shock will not only be scientific, it will be existential. For to know that the universe contains black holes is to know it contains extremes. But to know it contains naked singularities, white holes, wormholes, and exotic matter, is to know that reality itself is negotiable. What then does it mean to be part of such a cosmos? What does it mean to think, to feel, to imagine, when the stage upon which thought unfolds may itself be unstable? The escalation of strangeness is not only a challenge to science, it is a challenge to meaning. If the cosmos harbors objects that undo causality, then the very foundation of understanding is at risk. And yet, within that risk lies awe. Because to stand in a universe where such things might exist is to stand in a universe that will never cease to astonish. When black holes first emerged from the mathematics of relativity, they were considered too strange to exist. Now they are taken as fact, confirmed by light, by X-rays, and by the trembling of space-time itself. But as with every great discovery, their confirmation has not closed the mystery, it has multiplied it. For if black holes are real, then so too might be the other creatures that theory has imagined. Objects born not from stars as we know them, but from the deeper possibilities hidden in the laws of physics. One such possibility is the boson star. Unlike ordinary stars which shine by fusing atomic nuclei, a boson star would be built entirely from quantum fields. Bosons, unlike fermions, do not resist sharing the same state. They can collapse into a single unified wave, overlapping like light itself. If a cloud of ultralight bosons were to gather under gravity, it could form a star made of pure quantum essence. Such an object would have no surface, no atoms, no familiar structure, only the smooth hum of a field bound into stability. Some physicists have even wondered whether boson stars could explain the nature of dark matter, hiding invisibly in halos around galaxies, vast in number yet nearly impossible to see. Another candidate lies in the idea of the gravastar. First proposed as an alternative to black holes, a gravastar is imagined as a shell of exotic matter surrounding a core of vacuum energy. From afar, it would mimic a black hole, bending light and trapping orbits. But unlike a black hole, it would have no singularity inside, no infinite density, no paradox. Instead, its strange shell would balance against collapse, leaving a hollow center filled not with matter, but with the tension of space itself. If gravastars exist, they could hide in plain sight, masquerading as black holes while preserving the laws that singularities threaten to destroy. Then there are the shadows cast by dark matter itself. This invisible substance outweighs the stars, outweighs all the ordinary matter we can see, yet it has never been touched directly. What if dark matter can clump into compact forms? Could it form stars of its own, dark and silent, hidden in the halos of galaxies? Or could it collapse into primordial black holes, objects not born from dying stars, but from the very fabric of the early universe moments after the Big Bang? Density fluctuations may have been enough to form black holes of every size, from microscopic grains to giants heavier than galaxies. If so, some of the mysteries attributed to dark matter might instead be the work of these ancient, invisible relics. String theory, in its effort to unite gravity with quantum mechanics, offers its own vision, the fuzzball. In this view, a black hole is not a void with an inside, but a tangle of strings, a fuzz of quantum threads replacing the singularity. Each fuzzball carries the imprint of information that falls into it, avoiding the paradox of information loss. The surface of the fuzzball radiates, not through Hawking evaporation alone, but through the complexity of its tangled strings. Here, the black hole is not a prison but a tapestry, every thread carrying the history of what it has consumed. If fuzzballs are real, then the image of the black hole itself must be remade, not as emptiness, but as a storm of quantum structure beyond human imagination. Other theories go further, imagining objects sustained by energies that should not exist in ordinary matter. Phantom energy stars, for instance, are built not on positive densities but on negative ones. Instead of collapsing, they expand against gravity, their cores resisting in ways that seem impossible. Phantom energy, if it exists, could even drive the expansion of the universe itself, accelerating it toward a future where galaxies vanish beyond reach. A star made of such energy would be not a fire, but a paradox given form, its very existence a rebuke to the normal order of physics, and still the speculation does not end. Some theorists have suggested that the strange objects we glimpse, the anomalies in pulsar timing, the gravitational waves that do not quite match expectations, might not belong to our universe alone. Instead, they could be leakage from others. If a multiverse exists with countless realities pressing against our own, then objects from those neighboring realms might leave imprints. A ripple in spacetime here, a signal that does not conform there. Perhaps what we call a strange, compact object is not an object of this universe at all, but the shadow of another cosmos pressing against ours. Each of these theories, boson stars, gravastars, primordial black holes, fuzzballs, phantom energy stars, and multiverse leakage, is an attempt to confront the paradoxes that black holes leave behind. They are not wild fantasies, but structured efforts to reconcile relativity with quantum mechanics, to explain dark matter, to resolve contradictions that refuse to vanish. And yet none are proven. They live on the frontier, balanced between credible physics and speculation. The search for them is not only a search for objects in space, it is a search for coherence in the laws of reality. Black holes left us with questions too vast to ignore. Where does information go? What lies beyond the horizon? How can space-time break without destroying meaning itself? These theories step forward as possible answers, each carrying both promise and unease. If boson stars exist, then the universe is filled with invisible structures built not from atoms but from fields. If gravastars are real, then black holes as we know them may not exist at all. If primordial black holes roam the cosmos, then the seeds of structure were sown not by galaxies, but by collapse itself. If fuzzballs are correct, then the inside of a black hole is not mystery but mathematics woven into fabric. If phantom stars burn with negative energy, then even the universe's expansion is tied to forces stranger than imagination. And if leakage from other universes is real, then our cosmos is not a self-contained whole, but a shadow among shadows. In the end, these theories remind us that the universe does not end with the discoveries already made. It stretches further, pulling thought beyond the boundaries of evidence into landscapes of possibility. The night sky is not only a field of stars, but a canvas of questions. And each theory, however unconfirmed, is a brushstroke on that canvas, painting the outlines of truths we may one day touch. The mystery does not fade, it deepens. Every attempt to solve it expands the horizon. And so science continues, not only measuring what is, but imagining what might be, knowing that in a universe as vast and strange as this, imagination itself may be the first step toward truth. The universe does not speak in words. It speaks in signals, faint, scattered, and hidden within the noise of creation. To hear them, humanity has built instruments that stretch the limits of ingenuity, devices tuned not only to light, but to gravity, to particles, and to vibrations in space-time itself. They are the ears and eyes of a species determined to pierce the silence of the cosmos. When two black holes collide, the fabric of space ripples outward like water disturbed by a stone. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, captured such a ripple for the first time. It was faint, less than the width of a proton, but it confirmed that gravity itself could be heard. Since then, LIGO, along with its partners Virgo in Italy and Kagra in Japan, has detected dozens of these mergers. Each one leaves behind a unique fingerprint, encoded in the rising pitch of space-time waves, and hidden within those fingerprints may lie clues to objects stranger than black holes. If the merger signal deviates from predictions, if the ringdown of the final object lasts longer or fades in unfamiliar ways, then perhaps the colliding bodies were not black holes at all, but exotic imposters, boson stars, gravastars, or something yet unnamed. The Event Horizon Telescope has taken a different path into the mystery. By linking radio dishes across the Earth, it created a planet-sized eye sharp enough to image the shadows of supermassive black holes. In 2019, it revealed the silhouette of M87 Now, a glowing ring of gas orbiting the abyss 55 million light-years away. 3 years later, it captured the shadow of Sagittarius A, the black hole at the heart of the Milky Way. These shadows are more than images. They are tests. Any deviation in the shape of the ring, any irregularity in the way light bends around the darkness, could betray the presence of something other than a black hole. A gravastar's shell, a fuzzball's tangled surface, the outline of an object the equations have not yet named. Other experiments listen to the rhythm of pulsars, neutron stars spinning with clockwork precision. By measuring their pulses over years, scientists have begun to detect tiny fluctuations in their timing. These shifts are the fingerprints of gravitational waves from supermassive black holes orbiting in distant galaxies. But the same arrays could also reveal a background hum, a cosmic chorus from objects that do not fit the standard model. If boson stars merge, if dark matter clumps vibrate, their echoes might be carried in that universal music. The search extends into the realm of high-energy messengers. Neutrino observatories like IceCube in Antarctica sink detectors deep into the ice, waiting for the faint flashes of light produced when neutrinos pass through. Billions fly through every square centimeter of Earth each second, nearly all without interaction. But those that arrive from violent cosmic events carry stories from places where light itself may be trapped. If a signal arrives without the expected black hole companion, it hints at something else, a process not yet understood. Gamma-ray telescopes, floating above Earth's atmosphere, search for bursts of the most energetic light in the universe. Some bursts align with the collapse of massive stars, others with the collision of neutron stars. Yet a few defy classification, their power unmatched and their origins unclear. Are they the signatures of magnetar flares, or are they the brief shouts of stranger objects? Transient windows into physics beyond the standard scripts. The present tools already stretch the imagination, but the future promises more. The Laser Interferometer Space Antenna, LISA, planned by the European Space Agency, will place detectors millions of kilometers apart, floating in orbit around the Sun. It will listen not for the short, sharp signals of stellar mass mergers, but for the deep, slow songs of supermassive black holes colliding across cosmic epochs. In those waves, it may also detect anomalies, frequencies that whisper of structures more exotic than any star. The James Webb Space Telescope, already opening its golden mirrors to the sky, has begun to see galaxies as they were near the dawn of time. Among its targets are the quasars powered by ancient black holes. If their light carries signatures that cannot be explained by ordinary accretion, then perhaps they are powered not by black holes at all, but by some other engine hidden in the infancy of the cosmos. New X-ray observatories are also on the horizon, instruments more sensitive than any before. They will map the violent regions around compact objects, tracking how matter swirls and heats before it vanishes. In those patterns, in the flickers and oscillations of light, deviations may appear, patterns too regular or too chaotic to belong to black holes alone. And then there are the experiments reaching into the smallest scales, probing the interface of gravity and quantum mechanics. Laboratories are testing quantum sensors, devices so sensitive they can detect the faintest shifts in space-time curvature. Others are building particle accelerators to recreate conditions of extreme density, searching for hints of quark matter, strange matter, or the exotic particles that could compose boson stars. The frontier is no longer only in the sky. It is also underground, in cryogenic detectors, in quantum laboratories, and in collisions that mimic the birth of stars themselves. Each of these tools shares a common goal. They seek to separate the familiar from the unfamiliar, the black hole from the imposter, the known from the yet-to-be-named. If a gravitational wave lingers too long, if a shadow's edge is misshapen, if a pulsar stumbles in its rhythm, then the verdict may shift. The cosmos may reveal that black holes are only one part of a larger family of strange compact objects. The implications would be profound. If gravastars are confirmed, then the singularity never forms. If boson stars are found, then dark matter may at last step out of the shadows. If fuzzballs replace event horizons, then information is never lost, and the paradox dissolves. Each discovery would not only rewrite textbooks, but redraw the architecture of reality itself. The investigation continues because silence is not enough. The night sky glows, hums, and trembles, and within those signals are the answers to questions as old as curiosity itself. The instruments grow sharper, the data more precise, the models more ambitious, and yet the heart of the mystery remains. For now, black holes stand as the icons of cosmic strangeness. But the next signal, the next image, the next detection may tell us that they are only shadows among shadows, that the true diversity of compact objects is greater than ever imagined, that the universe, in its vast silence, has been holding back revelations stranger still. The tools are ready. The tests are underway, and the night waits, filled with signals yet to be heard. For most of modern science, black holes stood as the ultimate mystery. They were the limit of imagination, the edge of understanding, the place where mathematics bent into silence and physics refused to follow. They were thought to be the final monsters of nature, as strange as reality could ever become. But discovery has a way of humbling certainty. What once seemed impossible has become routine. The shadows of black holes have been photographed. Their collisions have been heard in the trembling of space-time. Their presence has been confirmed not by whispers, but by the loud signatures of a living universe. And yet, instead of ending the story, each discovery has expanded it. Black holes no longer look like the conclusion. They look like the first doorway into a deeper labyrinth. If stranger objects exist, boson stars of pure fields, gravastars hiding hollow interiors, primordial relics from the dawn of time, or wormholes piercing the fabric of reality, then the laws of nature may be broader than human reason has ever allowed. Perhaps the universe does not operate on the tidy boundaries of familiar physics. Perhaps it tolerates infinities, tolerates negative energies, tolerates structures that should never be stable but endure nonetheless. Perhaps the cosmos does not follow rules. Perhaps it is the rules themselves that are local illusions, temporary scaffolds built on a deeper strangeness. Such reflections are not only scientific, they are philosophical. They remind us that every law humanity has ever written into nature is provisional, a draft awaiting revision. Gravity once seemed absolute, until relativity revealed it as curvature. Atoms once seemed indivisible until quantum mechanics exposed their inner dance. Now black holes, once the edge of reason, may prove to be only milestones on a greater path. If they are not the strangest objects in existence, then the concept of strangeness itself must be reimagined. For what does it mean to live in a universe where even infinities may be exposed, where time can fracture, where energy can run negative, where other universes may press against our own? It means that the cosmos is not only vast in space, but vast in possibility. It means that reality is not a single story, but a library of narratives, many still unread. It means that human imagination, for all its daring, has only begun to glimpse what creation allows. The emotional weight of such a realization is profound. To stand beneath the night sky is to sense both insignificance and wonder. The stars that seem still are burning, dying, and collapsing into forms beyond comprehension. The darkness between them may not be empty, but filled with objects more alien than any dream. And humanity, fragile and brief, stands at the shoreline of this cosmic ocean, looking out across the waters. Black holes were once the deepest shadows on that horizon. Now they appear almost familiar, lighthouses of terror that at least obey their own boundaries. Beyond them may be landscapes where even boundaries dissolve. The question is not whether such things exist. The question is whether the universe has already shown them, hidden in the anomalies, the glitches, the signals that do not quite fit. If so, then the story of physics is far from finished. The story of wonder is only beginning. The final reflection is not of terror, but of humility. Because the universe, in all its violence and beauty, continues to outrun imagination. Every discovery, instead of closing the book, opens another chapter. Every answer deepens the question. And every horizon, no matter how final it seems, gives way to further horizons beyond. Black holes were once the icons of the impossible. Now they are gateways. Gateways to a cosmos more intricate, more unsettling, and more astonishing than thought can yet contain. And so the narration closes not with certainty, but with a question. One that lingers in the silence of space, in the shadows of stars, in the patience of time itself. If black holes are not the weirdest objects in space, then what else waits unseen in the dark?